Previously, we saw how to examine the distribution of data values for a set of sample observations by calculating the minimum, maximum, mean, median, and mode. And then we visualized those distributions using a histogram and a box and whiskers plot. Here's the histogram that shows the distribution of temperature scales in our sample. The mean, median, and mode are clustered at the center with symmetric tails of progressively less frequent values towards the extremes. In other words, this is a normal distribution. Now, looking at the values, you can see that there's some variance between the daily temperatures. But how can we quantify that variance? Well, one way is to calculate something called, you guessed it, variance. And the formula for variance when working with the full data population looks like this. We calculate the sum of the squared differences between each value and the mean, and then we divide that by the number of observations. We need to use the square of the differences, otherwise we'd end up with 0. We indicate the population variance as sigma squared. In Excel, you would simply use the var.p function. However, in this case, we're dealing with a sample of data, not the full population, so the formula is slightly different. We subtract 1 from the number of observations we're dividing by to allow for bias in the sample, and we refer to the variance as s squared. In Excel, the appropriate function for a sample is var.s. In this case, that gives us a variance of around 172.27. But what does that actually mean? 172.27 what? Now the problem is that because our value is squared, it's no longer in the same scale as our data. So what we can do is calculate the square root of the variance to calculate something called the standard deviation. For the full population, the formula looks like this, and we indicate the standard deviation using the Greek letter sigma. And in Excel, you would use the stdev.p function. For a sample, we indicate the standard deviation as s, and we calculate it in Excel using the stdev.s function. Now that gives us a standard deviation for our temperature data of around 13.13 degrees. Now that gives us an idea of how spread out our data is. The higher the standard deviation, the more variance there is between temperatures in our data sample. Now remember that I said statisticians love a normal distribution? Well, here's one of the reasons. In a normal distribution, the mean is in the middle, and around 68.26% of all observations lie within one standard deviation above or below the mean. Around 95.45% of observations lie within 2 standard deviations of the mean, and around 99.73% of observations lie within 3 standard deviations of the mean. So by knowing the mean and the standard deviation, we get a pretty good idea of how the data in our sample is distributed, allowing for variances in the values.